Alright, chemistry nerds, so here we are for version 2 of our polymerization and polyethylene video, and this is the one we want you to focus on. As you're aware, here are our dot points that we'll be focusing on today, and let's get into it. So what's the point? Basically, you want to be able to differentiate between monomers and polymers. You want to explain the process of polymerization as a flowchart. Now, I'm not going to do this for you. You should be able to take your notes today and put it into the separate steps. You want to differentiate between HDPE and LDPE, and this means, in this context, I want you to be able to conditions that it's formed under, properties of the products, etc. Okay, so it's more than and description of the chains. It's more than just this one is tightly packed because it's got branching side chains and so forth. So, usefulness of ethylene. Now, ethylene itself is actually quite useful, and that's why it's in such high demand, and this is why we need to crack our sources from, say, natural gas, the larger chains of hydrocarbons down to ethylene. It's really useful. We can polymerize it to make polyethylene, we can oxidate it to make ethylene glycol or polyvinyl acetate, we can halogenate it to make PVC, polyvinyl chloride, or ethyl bromide, which is really good as a refrigerant. We can alkalize it to make polystyrene. This is super useful. And we can hydrate it to make ethanol, which is useful for more than just beer. We can also use it to make solvents for industry, antiseptics, etc. This is a really good chart, and I suggest you draw this down. So just showing a quick summary of the uses of ethylene, the different things we can do to it. Now, monomers and polymers. Basically, polyethylene, or polyethylene, is a polymer of ethylene, or ethene. Remember, those two are used interchangeably. Now, a monomer is one individual small molecule that can be joined to other similar or identical molecules to form a chain. Okay, that chain becomes a polymer. Polymer means many. Now, the polymer itself is a large molecule, a long chain consisting of smaller identical units joined together. And it's those smaller identical units that we use to identify it. So we name it based on that, and we usually put poly on the front of it. Not always. Like DNA is deoxyribonucleic acid. We don't tend to call it polydeoxyribonucleic acid, but we could. Now, there's polymerization. So this is the process of making a polymer. Now, we're going to focus on two this course. One will be addition, which is what we're going to talk about today. And then there's condensation, which we'll get into when we talk about biopolymers like cellulose. Now, monomers of ethylene are joined together to make polyethylene. So we'll just go for a quick breakdown of how that happens. Or actually, first, when you draw a polymer in an exam, or whenever we ask you to draw one, draw at least 3 subunits. If we ask you to give the structural formula for it, this is not bad, like over here. But if you're drawing it, 3 subunits. Now remember, polyethylene, that this group here, that is a subunit of it. So we use an initiator, and that's what gets the ball rolling. The one we're going to talk about today will be dibutyl peroxide, which if you see here, you've got the O on there, which is what makes it the peroxide. This is one unit of butyl peroxide. This is a separate unit of butyl peroxide. Now, the initiator splits, forming 2 free radicals. So this bond here breaks, and this gives a free radical. Now remember, a free radical is a unit that has, so it can be a molecule or even a single atom that has 1 free electron. And it makes it extremely reactive. And in your body, these can be quite destructive, which is why we have a whole system of antioxidants in our body that takes care of them. You don't need to buy antioxidants, you have them already. So it forms 2 free radicals, and one of these free radicals will bond to the end of an ethylene. Now the way it does it is it breaks this double bond and it joins there. So we get this C4, actually it's the O end that joins it, but C4H9O, but it's joined there, and that double bond is broken. Now, what this actually means is, because there's no hydrogens to fill this up, you've now got a spare electron at the end, so that becomes a free radical. How does this carry on? Well, we'll get to that in a second. I want you to think about why we use ethylene instead of ethane. So why ethene instead of ethane or ethylene? Alright, the free radical process to make LDPE. So this is addition polymerization of ethylene. Now it requires heat and catalyst to break up the double bond of the monomers together. In this case, we're not talking about a catalyst, we're going to talk about the free radical process. So you can actually get rid of that line there, we don't need to worry about that one. Now it's subject to high temperatures, about 300 degrees Celsius, and intense pressure, 100 to 300 megapascals. So then we put in the initiator particle, and this is what we do. So initiation happens. So the initiator starts the reaction. This bond here breaks. We now have two of the free radicals. R here just represents the group that comes off it. So in this case, it is a carbohydrate group coming off the oxygen. All right. Then we go to activation. So we've got our free radicals. It's put in with the monomers, and it forms an activated monomer. So what this means is this free radical joins here. Now remember that double bond is there. It breaks that double bond. So we then go oxygen R. That double bond is now broken, and we have a free electron there. Okay, so it turns this monomer into a radical. This monomer becomes a radical. All right, so that's activation. Then we have propagation. So that's when the monomer radical collides, and this is why it's done at a high heat and a high temperature and a high pressure, so that more collisions will occur. It collides with more monomers, and this free radical here breaks the bond. The monomer joins, so we get another CH2C H2 free radical, which will then bump into another monomer, which will join, which will then bump into another monomer, which will join, which will then bump into, and so forth. And we get polymer free radicals, so we get long chains of free radicals. Termination. Now, chain growth terminates when the free radical chains combine. So a polyethylene molecule is formed. So this long chain here and this long chain here, both with the electron to share on the end, when they collide, the chain terminates. Like the reaction terminates, and we have a long, stable polyethylene molecule. One thing that does happen though, is if another free radical comes in here, it can strip away hydrogen. It comes in, strips away hydrogen, bonds, and we've now got a long polyethylene with a large side chain hanging off it. Bonus side chain. This is what makes the free radical process low density. Okay, so that's what makes it low density polyethylene. All right, catalysts. Now, so catalysis gives us high density polyethylene. So a catalyst equals a lower activation energy. So we do it at lower temperatures and pressures, and this means that this gives us reduced production costs. Okay, now the use of a catalyst results in the growth of long and unbranched chain polyethylene, which we call high density polyethylene. Sorry, that was tough. Okay, so we see as we go along here, there's no long branching side chains, so they can actually pack in nice and tight. Alright, so then we've got the ZIEGLER-NATTA catalyst. This was a triethyl aluminium, and it's used to manufacture polyethylene, in particular high density polyethylene. So it works with titanium atoms, and these two guys, Carl Ziegler and Giulio-Natta, shared the 1963 Nobel Prize for it. Here is the process. We went through it in class, and if you don't really need to know that process, but that's what it is. Basically, it forms a large complex here. Along comes the polyethylene, it bumps into it, okay? It then rearranges, and you've got it up there. Then it bumps into another ethylene, which is rearranged and added on to this one here. So this now gets larger and larger, and that repeats many times. Now, that happens slower and a more relaxed process, and this allows the growth of long chains of polyethylene that are straight without all of the extra chains. Because it rearranges it itself, you don't have the free radicals just bumping into it and joining to the side. And that's how we get high density polyethylene. Alright, so polyethylene types. Let's go through these very quickly. High density polyethylene, linear chains with few to no side chains, allows very tight packing. It's defined by a density of greater than 0.941 grams per centimeter cubed. Remember, water has a density of 1, so it's still less than water. It's used to make bowls, buckets, and containers. Generally, it's quite tough. Also brittle. Like, it's more brittle than low-density polyethylene. So, LDPE. Basically, it has branched chains. This allows the packing to not be as tight. It's less strong because of this, okay? So the intermolecular forces, basically because the instantaneous dipole-induced dipole attraction is less, the intermolecular forces are not as strong. So it's not packed as tight. This results in a lower tensile strength, so you can pour it, you can rip it apart, but it gives you increased ductility, okay? So it's for different uses. So it's got a density of between 0.91 and 0.94 grams per centimeter cubed. And it's flexible, still strong, not as strong as high density polyethylene, but strong, so we use it for plastic bags, electrical insulation, anything that needs to be drawn, like a wire. Your cling film is always low density polyethylene. So here's a quick look at the two differences. Obviously, we've got We've got the long branches here, but you've got the chains coming off the top. So this is low density polyethylene. Whereas this one is quite linear. This is the high density polyethylene, and it's straightforward. That's what it looks like. Alright, here is a summary of the differences, basically about the conditions which it's formed. You need to have this. Alright, general properties of polyethylene. It's insoluble. It's stable, or insoluble in water. It's stable. It's inert, which means it's really good for storage of reactive chemicals. And this is why a lot of containers are made with polyethylene. Large number of dispersion forces, so this means it's tough and strong, especially with the physical tangling. Thermoplastics can be recycled, so they're melted and reformed into new shape. These are all HDPEs, and they have to be because they've got no side chains, they're able to, as they melt, slide past each other without tangling. Alright, that's it. Enjoy. I know that was long, and I'll see you in the next one.